Hi, good morning. So, how's everyone doing? I'm sorry I couldn't be here on Wednesday, and now the lectures are kind of, I left off something on Monday which I need to finish before continuing on with whatever I was going to do today, right? And one of the reasons I hate that video lectures is I was just talking, in a room with nobody else, so I don't know how fast I was going or what have you, right? So was that stuff we covered on Wednesday clear? Right. We're going through a lot of technologies about hardware, hard disks and so on and so forth. So so that's the stuff from your textbook in terms of how the hard disks are arranged and stuff like that. And later in the course, I'll kind of give you a hint of how real hard drives are. I mean, real hard drives are a little bit more complex and stuff, right? So some of the things that we'll talk later in the class today may or may not be applicable, right? For example, this still have the platters and stuff like that, but there's a little program firmware OS component running on the hardware, which is trying to do some optimization. Hard disks have local cache, and that can do certain operations better or what have you, right? So some of the stuff that we look at from the OS may or may not be true because the disks are smarter. Disks are not that dumb, right? But regardless, the techniques we look at are interesting, right? So I'm going to go back to first go back to the file system implementation stuff we were covering on Monday and wrap that up, right? So essentially we were trying to see how you would organize implement a file system. So you had the notion of directories and disk allocation and free blocks. How do you know free blocks and stuff like that, right? So we looked at some of those things, and now I want to add some other features which are important, right? So do you remember where we left off? Right. So the first component is the efficiency in terms of how good a file system is for whatever task you're doing, and that depends entirely on the kinds of files that you're going to access, right? And it's kind of seems obvious, but so if you look at the Unix inode structure, which has direct, some level of direct block, some level of one level index, two level index, and triple level index, right? How good that is depends on the kinds of files that you're going to be accessing, right? So so it was designed with the assumptions that lots of files are small, but there are few huge files. So you need to be able to make it fast for the small files, which are many, but you need to be able to support large files which are not that many, right? So you have this triple level indirection infrastructure. But if you're operating on different kinds of objects, if you're a file store for multimedia objects, and each one of them is like gigabytes large, right? You may design those things differently. So so your file system design depends on the kinds of files which you don't really know. So you kind of go back and forth. You try to do lots of analysis and stuff. More generically, caching plays an important role. Caching in terms of reading something ahead of when you're going to use it, right? Caching or prefetching are good things, and the other stuff is if you knew what kinds of access you're going to do, the file system can do something different. And one of the things was what I mentioned in the homework assignment, right? So if you know you're going to access files sequentially all the time, so I know if I access block 1, I'm going to access block 2 soon, I'm going to access block 3 soon, and so on. So I could potentially read those before I need them, right? And that's the notion of the read ahead. So I read before I actually make a read, right? And if you win, if the pattern actually follows what you're trying to do. And the free behind basically says that if you know that I'm going to read 1, 2, 3, 4, 5, 6, whatever, so the replacement policies can throw away the pages after I'm done. So you don't have to cache stuff. If I did 1, then I went to page 2, then I went to page 3, you could potentially free the page 1 because you know you're not going to come back to it, right? So depending on how you set this stuff up. So depending on what kind of application. So that's the high level theme in, I want, hopefully you take away from the operating system class, right? There are a lot of techniques we learned, but essentially what we're trying to do is trying to match what the applications do with what the operating system tend to do, and that's true for here too. And there are certain, so some of the stuff people noticed are there are certain files which last for a very small amount of time, right? So for example, if you're doing a compilation, right? I don't know how many of you have taken a course in compilers, but essentially you have multiple different phases, right? You have a compiler, assembler, linker, or what have you. So essentially what happens is you take a C program, there is one program which reads it, does some processing, and creates another file, which another program would read, assemble it, create another file, which makes, object loader would read it and create a program and so on, right? So all these intermediate files don't last for too long, and those you create. So if those are not going to be around for a long time, if they're not visible to the user, right? Then you want to give the best performance, and you have a notion of a RAM disk. Essentially, you take some piece of memory, main memory, make them into a file system, right? And so that won't be persistent, but it'll be very fast. There's no C kind of thing. So that's one thing people have done, right? To solve the problem of what do you do when the files don't last for too long and you don't really care about the persistence. So at this point, I'd like to get back to stuff that we actually didn't cover when we were doing the virtual memory section, because I didn't really think it fitted at that point, right? So there is another abstraction of how you can use the files and virtual memory. So the idea here is when you do virtual memory, essentially your virtual memory system was reading pages off. So on demand, it'll read some page off of the disk, and it'll write dirty pages back to the disk, right? So that's what we were doing in the virtual memory. We are trying to create a larger memory by moving stuff back and forth between the hard disk. And in the use of file systems, you're doing the same thing. The user is reading files, writing files, what have you, right? So one of the variations people thought about was, if you can, since the OS is already doing all the virtual memory stuff, if you can map the files into a virtual memory construct, right, then you don't have to figure out all the reads and writes. You can let the OS deal with all the reads and writes and go from there, right? And that's the notion of a memory map file, right? And I'll send you a little sample program of how you do that in C. Essentially, what you do is, so suppose you have a right, and suppose you have a file called file.c, right? So and this is the C way of doing it, right? You do a mmap, right? There are some things you have to do. You have to first open the file and so on, right? But conceptually, you do this mmap, right? And then you can do unmap, right? So once you do this, and there are intricacies on how, it has a bunch of arguments and stuff. So essentially, you can say, I want this pointer to point from, say, here to here. You don't have to map the whole file, right? You can set up more variants of this, right? For now, assume that you can basically say this pointer now points to this chunk of memory, right? And you can set up what kind of permissions you want on them. You can set them to be read only, write only, execute only, and all those things. So essentially, the pointer now becomes pointing to this whole file, right? So if you say star ptr equals a, right? When you do a unmap here, essentially this byte will be A, right? And this is similar to what you would do as write A and close, right? Except explicitly you say when the object should go to the disk and so on. This is the typical way you would implement this using a file abstraction. But if you're using a memory map abstraction, you would map the memory segment into your address space, and then you operate on it like it's a normal pointer. You don't. So it behaves like how you would have gotten it if it was a malloc structure, right? You can write to it, you can read it to it. So if you do lots of star ptr, say equals b, right? You have no idea when it'll be flushed to disk. So the write may happen here to the disk. The write may happen here. You just know that when you unmap it, things will be consistent. Right? So you can do a lot of cool stuff. So if you have a structure, you can actually leave pointers here, right? So you can actually say equals some pointer, or right? And this is usually something that you don't do, and essentially you're leaving a pointer into your file, right? What that means when the program runs again and all is up to you, but you treat this chunk of memory as something into your process, right? And the reason why people like that is the OS is already doing all the stuff for you. So why should you bother to do this read and write, which are where you're explicitly saying when something should go into memory, when something should get from memory, and all those things. Since the virtual memory system is already doing all the stuff for you, why not just use it, right? And that's the reason why people like mmap. And it's kind of a construct which needed for you to understand what files are and what virtual memory is, and so I kind of moved it from virtual memory to this point. So this is one of the constructs which actually your program will use whether you realize it or not, right? So your libraries tend to use a lot of this stuff to read stuff from the disk rather than trying to do a read and write, right? And we'll see some of the problems with doing it this way, right? So there is another system call which we're not going through in class, which may help you try to figure out what is really happening with a program, right? Which happens in Linux, and I'm not sure what the equivalent in Windows is. So if you want to see what system calls your program is operating on, right? There's a function called strace. It depends on the operating system. So in Linux it's strace. I think in Solaris it's truss, right? So if you run your program like this, I mean, strace is a pretty powerful command. It gives you a whole bunch of options, but it tries to tell you what you should look at and stuff, right? So essentially it prints all the system calls that your program is making. So it's not directly related to this class, but it's a good tool for you to see what the actual program does. So if you do strace ls or strace one of your programs, you can see all the system calls that are being made, and some of them you won't recognize because they're being done by library calls and everything before your program runs, right? And that tells you the whole sequence of libraries being read and all those things. And that's one good way to see what an actual program does, right? And I'll try to send you a little bit more stuff by email, right? And it's not related to the class, but it's a cool little tool to see what your program is doing, right? And I'm sure there's something similar to that in Windows. I'm not sure what the command is for Windows. For Mac, you do ktrace, which is a kernel trace, and then you print the output. So if you do this, you could see that your program actually calls mmap and all those things internally without you using explicitly, right? But so mmap is actually much more powerful than what I just mentioned. So you don't have to say the whole file. You can say, I'm just going to operate on only a subset of the file, right? Only subset of the file should be mapped. So if you try to access this area, you'll get a segmentation fault. So you can kind of say only this part of the file will be modified. And I can also set the it's virtual memory, so I can set the virtual memory kind of stuff. So I can say this will be read only, and this will be read write, and this is read write and execute, right? And so you can do a lot of simulations and stuff using these models. So you can actually implement some of the stuff we talked about in class by setting the pages to different things. So if you try to write into this, you'll get a segmentation fault and what have you, right? So look through mmap to see what are the things you can do, but essentially it tries to map the whole thing in. And that's the logic here, right? Since OS already knows all the stuff, why not let it do that? And so once you can do this, once you can do the virtual memory and stuff, you can also share. There's nothing which prevents you from sharing. So you can create another file which also maps the same thing, right? And operate on it, right? It's supposed to be memory. So depending on how complicated you want to make it, right? You could have a really powerful system, or you could shoot yourself in the foot. So if this also maps it as read write, you better make locks and stuff because you're now operating on the same construct. If this is operating on read mode, right? Then all the things we looked at in virtual memory, you can have multiple readers, single writer, what have you. You can implement all of those using this particular model, and so you can essentially do sharing at the byte level using these constructs. So sort of like your book has a figure to mean how that looks like. So a disk file which is at and with mmap you can also, if you're more advanced features of mmap is you can say where you want this pointer to be, what address the pointer should be mapped to, right? So you can make sense of these pointers and stuff. So this particular disk file which has like 6 blocks out here, process A and process B have mapped them into their address space in certain fashion, right? In the virtual address, it's laid out like that. On the physical page, it's laid out differently. So they continue to operate on that like it's a memory page, right? And all the stuff we talked about in virtual memory would apply here, and they tend to be wherever in physical memory and stuff like that, right? So this brings up an issue of what happens when you do caching. Right? So the idea of caching is when you read a block or when you write a block, you want to keep that in main memory so it can be used by somebody else, right? And that's the generic form of using caches. So in this case, if these two processes are mapping this segment and they're operating on it, so there's a cache which keeps these values till it's actually have to be returned to the disk and stuff. So if another process comes here and opens this, let's say this process, right? This process is opening the file as read write using the traditional file I/O primitives, right? So now you could potentially have a problem. If you're treating mmap as a separate mechanism, then mmap would have its own caches where it keeps all the writes. And now if you try to open it using the normal read write call, you have to unify all the cache. So you have to have one kind of cache which will be used by the virtual memory system and the file notion. Does it make sense? So all the mmap system goes to the virtual memory system. And the virtual memory system can have its own caches in dirty pages and all of those things, right? And now mmap essentially blurred the difference between files and the virtual memory system. So if the virtual memory system was to have its own caches and the file system wants to have its own caches, you could potentially have a problem if you mix and match both, right? So if you use only the page side, you're fine. Virtual memory side, it's fine. If you're using only the file system thing, you're fine. Otherwise, you could end up having two caches. You could end up having the same page cached once from this side, once from this side, right? And kind of figuring out how to mesh those things. And that's the notion of that's the problem we address here. So essentially, your memory map I/O would have its own page cache, right? And from the page cache, it essentially has to go to some kind of a cache which works with the disk. So we call it the buffer cache, right? So every time we do a I/O, it has to go into some buffer before it gets flushed to the hard disk, right? So now you have two levels of cache. So things could be on the page cache and things could be on the buffer cache. So something which is operating on the file can operate on a different set of cache, and then the page cache, right? There is no clear picture of what should happen, which should go through. So if this is what is happening, right? What may happen is the page cache may have a value for this as A, right? The buffer cache may have value for this as B, right? The OS makes no guarantee whether the A is right or B is right. So what you're worried about is the fact that there has to be two cache holding this stuff. You're not worried about the correctness of this program. So if you have a program which is operating like this, there's two memory map stuff. One is writing, one is reading, and you have another process through a file writing into the file, right? The results are undefined from the OS perspective. You have to implement locking and stuff to make sure that people are not operating on the same space, but the OS makes no guarantee, right? OS makes no guarantees whatsoever for sharing and stuff. You have to use the locking and stuff just like we did before. So we want to avoid this stuff. So that's the notion of a unified buffer cache. So most modern operating system, modern in the sense of the last few years, tends to have unified buffer cache, right? The latest version of Linux, latest version of FreeBSD and stuff would do a unified buffer cache where you have the I/O routines and the AMAP routines operating on the same set of same buffer, right? It's not that old a phenomenon. It's a fairly new phenomenon. So if you ever read through the specs of an operating system, more like a Linux kind of thing, right? You would notice the word buffer caches fairly recently, but that's the idea here, right? You're providing different abstraction stacks is the same thing, and you're providing the same cache. Yes?
So then what exactly did the page cache do again that was like different than what the buffer cache been used?
So the page cache, so if you assume that this is going to, this way of accessing stuff goes to virtual memory, right? So virtual memory has to, this is the stuff we did in the previous module, right? So it has a notion of a cache and everything, and then it eventually when it has to go to the disk, it'll do a read or write, right? So that's the page cache is the cache we talked about there, right? From the virtual memory system, when it does a write, it does not care whether it actually goes to the disk. It just says write, right? So the buffer cache is essentially the file system or the disk system cache. So they don't have to be separate, but they are separate because they come from different modules, different things. The virtual memory system assumes that if it wants to read something, it says read. If it wants to write something, it says write. It doesn't care how many caches it goes through. Okay. Does that make sense? Mm-hmm. So the part that all these things simplify is the file system looks like a monolithic block. The file system looks like a square block where it is assumed to do some sort of stuff that we looked at on Thursday, right? It's a file. There's no cache kind of thing, but real hard disks have a cache there. So if you bought a disk lately, right? One of the things that parameters that they'll say is it can have 8 meg or 16 meg or some level of cache, right? So how many of you bought or looked into any disk recently? So if you look into a disk, disk come at least with 2 megs of cache, more reasonably for 8 meg, and most of the newer disks comes with 16 meg, right? So essentially, there's a cache between what your OS is sending and how it actually goes into the hard disk, how it actually goes into the platters and sectors and all that stuff, right? That has implications of some of the stuff that the OS tries to be smart about may or may not really help because there's another cache which is filtering these things. Right? So from the OS perspective, once you unify these things, right, you don't have to have 2 copies, right? So, but the implementation details of doing this stuff means that now the virtual memory system and the file system, which operate at a much different fashion from the user perspective, have to all map into something in the same fashion, right? I mean, you typically assume that files are different than memory, right? How many of you used a memory map files before? I think it's a little easier to use in Java than in C, because it's much more powerful in C than in Java. If you haven't used it, it's a pretty nifty way of using files, right? Without having to worry about the details of read and write. You can just treat it like your normal program. So, but once you start using that, a lot of people I know who start using memory map file never want to go back to treating it as a file, because now it's pretty liberating, right? You can allocate an array, right, and operate on the array. You can essentially call this as an array and then operate on this like an array, and never have to worry about when things have to be written back. Once you do an unmap, everything is going to disk, but you don't have to actually figure out, So if you operate on a 2-dimensional array, right, most of you would have written code where you say, for I equals 1 through j, you go through, say, each row or something and write each stuff, right? Or you write the whole thing, then you have to figure out how to read them back and everything, right? But now you can, right? How do you write this to disk? I guess in Java you can serialize the whole thing, right? How do you write this, like an array like this to disk? You could write it all in one go with the whole buffer, right? But you have to read it back into the same kinds of structures, so there are little problems with that. But if you use mmap, you don't have to worry about all that. You create a buffer, you create an array, and you would read it and use it in the same way, right? So the next 2 things it concerns recovery, right? So we talked about all the file systems and stuff. We talked about all these structures that you create and stuff. But file systems, so when the machine crashes, all the things we looked at so far in terms of CPU and virtual memory and memory management and all those things, right? When the machine crashes, you don't have to worry about stuff being inconsistent, right? If your page table was kind of not updated properly, but if your machine crashes, when you come back, you typically start with a clean state, right? Very few times do you start with where you left off, right? Again, this may not be true going forward, right? But for now, you can assume that typical desktops, when you crash, you kind of wipe out the whole thing, right? Why I say it won't be true is, like, in the future, when you have like lots of memory laptops and stuff, there's a move towards saving all the state so you can boot up quickly, right? The more memory you have, the more disk you have, the longer it takes for you to boot up. So one of the ways that people are trying to make this stuff faster is to kind of use the same stuff. But in general, all the memory can be thrown away, all the stuff can be thrown away, you don't have to worry about the stuff. Whereas disk is not true. Disk is, everything is in the disk, so when you come back, you read back from the disk. So if you don't have the right set of stuff on the hard disk, then, so you need to essentially recover from what you did, right? So you need to be consistent with what's in the disk. So one of the popular ways to deal with that is through a log structure file system, right? And log structure file system uses some of the logging techniques we talked way up in the front, right? So essentially, we know that all the file operations have to go to disk, right? And which means that it has to, your head has, the disk head has to move somewhere, whatever, and put them in the right context and stuff. And there may be a lag in how these things go to the disk and everything. So you maintain a log structure. You maintain all the operations that you're doing as a log, and have a background process which reads from the log and moves them back to where they ought to go in the disk. So you implement all the stuff we talked about before, right, in terms of allocating inodes and blocks and all those things. But when you actually have to go to the disk, right, keep writing them as a log, keep writing all the operations back to back together, right? So when a system was to crash, you essentially have a transaction log on the disk, which says that you opened a file, you write, but then you crash, you didn't finish the transaction, right? So you can use the transaction principles to either go back to what the state was when it's open, right? So you can do a lot of cool things. You can say, when you do a close, then I'll go through the log and then write everything back, right? So potentially you could do the operations twice. Write the files into a log, and then read from the log back into the where you want to go, right? And like I said, it's potentially you do the operation twice. But the good thing is, if the machine was to crash in the middle, right, you are in a much better position to recover than what you were before, right? And there are lots of variants of this idea, lots of variants of how to avoid writing stuff twice. If you do it a certain way, you don't have to write it twice. But essentially, the idea is you don't actually modify the real stuff, because once you modify the real stuff, then there's a very hard way to undo. So if you write it to a log, then you can undo it. If you're writing to a log, then essentially it's a serial operation, right? So this does not have to go back and forth and seek. So your real file may be all over the disk, but the log can be all in one go, right? And most of these techniques are already in your operating system. Your newer in Linux, your ext3, exfs, and racefs, and all those things basically do some form of logging, right? Logging the metadata. So the variations in the operating systems, different file systems, are what they log for performance reasons and stuff. But essentially, these tools are more and more popular in more of the newer operating system, especially when you go mobile, right? If you have a laptop or one of those, something which is mobile, then it's highly likely that you're going to run out of battery power. You have to crash in the middle. It's highly likely that your battery falls off. It's highly likely that your machine will just crash, right? So having a log structure file system can potentially save you a whole bunch, right? How many of you are aware that you are running a log structure file system on your, which one do you use?
I use OS-10, so
okay.
it's just the standard German.
Yeah, OS-10 does that, and Linux it probably does. I mean, many of you, I remember some of you said they use Linux, right? I'm guessing you're using ext3 file system, right? What do you use?
XFS.
Okay, so yeah, ext3, XFS, RacerFS. Most of the modern file systems would do some kind of logging, right? So going into the exact details of what XFS does is way beyond the scope of this class. So you can't really log everything, right? Which means that you do everything twice, and you may not have the resources to do that, right? So most of these file systems only log the directory entries, not the actual data. But you can actually tweak you can set parameters to make it log everything. Then your system will be running half the speed, taking twice the bandwidth, battery capacity and stuff. Right? But anyway, so those are that's the optimization. Right? So that essentially completes the stuff about the implementation. Right? There are lots of newer things, a lot of things that come into the fore because of how we do these operations, right? Like mmap and stuff adds new complexities. So so those are the issues of. So in the previous chapter, we looked at what files are, what directories are, how they're organized, and stuff like that. And in this chapter, we were looking at how would you map some of the constructs that we talked about in the previous section into an actual storage media, right? And unfortunately, I'm supposed to go from here to the Wednesday lecture where we talk about the different hardware technologies and stuff. We kind of went before that, right? So at this point, we're not really worrying about how the hardware technologies are, but how would you lay the structure? How would you write and read the contents, right? So is that clear so far? So I'm now going to go back to the continuation of the yesterday's class, right? And the stuff that I didn't actually go through in the lectures, right? So the idea here is, we talked about, let me place this stuff. So right, so you have, a hard disk is made of platters, right? And you have tracks, right? And then you have each track is separate into sectors, right? And then you have a notion of cylinder where it's the same track and all the different platters, right? And then you have a logical notion of a block, which basically says that, so you can name this as this is block 0, name them all the sectors in this block, and then all the sectors in the cylinder, right? Before going on to the next track and so on, right? So essentially, this way you map the cylindrical form of the hard disk into something which is linear, something which is very defined as blocks and stuff. And typically, the hardware supports 500 byte sectors, but the operating system lets you choose the block size that you want to operate in. And the choice depends on how much fragmentation you want to see. So if you use a 512 byte block, then you don't waste space, but you could potentially spend a lot of your time on seeking and stuff, right? So you could make something larger. So you can, typically I think they use 8K, you can have 64K or whatever. So essentially that will mean that a whole bunch of sectors appear to the OS as one logical block, right? So that's the hardware technology of how these things work. So the next notion is trying to figure out how to do scheduling such that you get good performance, right? So in this setup, there are two things which kill you. One is the rotational latency, and then another one is the seek, right? Rotational latency basically says that if you have a disk arm which is here, and the disk is going this way, right? So if I wanted to read this particular sector, rotational latency says that the disk cannot read it till the disk rotates around and this comes right under the head, right? So you can only read stuff under the head. So if I want to read something here, I have to wait for the disk to rotate around and come below me, right? So during this time, you could potentially be sitting there doing nothing, right? And that's what you're trying to solve. So essentially that's rotational latency. So it depends on how fast the disk is spinning. So if you have faster disk, then you avoid this rotational latency, right? And that's one of the reasons why you want to buy a faster disk rather than a slower disk, because faster disk would help you save on this component, right? The seek latency is you can kind of move this head on this axis. So instead of reading here, I could read over here, right? In which case, I need to move the head from this cylinder to here, right? So the disk head can move on this stuff back and forth. So essentially, I have to move here, right? So if I want to if I'm at this point here and I want to read something over here, right? I need to do a seek from this track to this track. Then I need to wait for this disk to rotate around to get to where I am, right? So this depends on how fast the disk is spinning. So faster disk will save on rotational latency, right? There's not much, whole lot you can do for the seek part, right? Even if you buy different hard disks, the effort of moving a physical stuff on the head, the technology is fairly stable. So regardless of the hard disk that you buy, this is same, right? And actually, usually this takes a lot longer than this, right? And it's got to do more with the mechanical aspects of it than the computer science aspect of it. But I think it's to do with the inertia of how these things work, right? The disk is spinning all the time, so you don't have to do anything to dampen the movement. But whereas if you're moving this little stuff, you have to know precisely where you are, right? All of these are highly precise operations. So instead of if the head being here, if the head landed halfway between these two tracks, right? Then you read garbage, right? So it has to precisely come to that point, and that technology is highly developed and highly complicated. So essentially you have these two components, rotational and the seek latency, right? So suppose you want to read, say, this, and say this, and then say this, right? And if you can read this, but essentially I want to read a whole bunch of blocks all over the hard disk, right? If I do it naively and then give it to you in the way that you wanted it, then for each one of them, potentially I have to do a seek, and potentially I have to do a rotational latency, right? And potentially that could be extremely slow operation because the seek and the rotational latency are very slow, right? So what we're trying to do is, how do we schedule these portions, right, by reordering these things such that I have to do the least amount of seeks and the least amount of waiting for rotation latency. Because while I'm waiting for the disk to spin to where I am, the disk is doing nothing. And while the disk's arm is moving, it's doing nothing, right? So how do I improve the throughput of the disk by making sure that I can schedule these operations properly? And that's the notion with this disk scheduling, right? So the way the book talks about it, it's done in the operating system, but more and more it's actually being done inside the hard disk or the hardware, because there's a firmware running there which is doing all this scheduling, right? But regardless, somebody has to do this. Somebody has to do that, because otherwise you're potentially, you can have, you know, one block in the innermost sector, one block in the outermost sector, outermost track. So you may be, you know, going back and forth, and that tends to be fairly low utilization, right? So let's take the case of you know, the trace over there, 98, 183, 37, and so on, and the head is at position 53, right? So the problem we're trying to solve is, given that request queue, how do you reorganize it such that you finish the soonest, you reduce the rotational latency and what have you, right? So the first policy is first come first serve. This is sort of what you're trying to do for your homework project, right? It's a first come first serve policy, right? Which basically says that I don't do any reorganization. I do it the way the hard disk is. So from 53, you have to pay the cost to go to 98, and then it's 183. So if you're assuming in a certain where these blocks are in the disk, you have to go all the way to 183, then you go back and go forward and stuff, right? And so this will incur a certain amount of seeks and rotational latency, right? And as you may expect, this will perform the worst, because essentially you're not using the fact that the disk has certain cost in moving in a certain direction, right? So there are different variations of this, of how you could solve that. The first one we look at is the shortest seek first, right? Which is essentially like a shortest job first policy, right? The hard disk knows all the requests it has, so it knows where the head is, so it can go to the one which requires the least amount of seek and go from there. So it can go from where it is. So if you run that algorithm, essentially this is the kind of trace you get, right? So from 53, instead of going to 183, you tend to go to 65, and you go to 67, and so on. So you reduce the amount of seek, right? Now all the requests are reordered, right? So if you wrote that trace into the hard disk, what is actually returned is not what you, in the order that you sent, but in a different order, right? But this essentially would reduce your seek time and get you hopefully better performance out of the disk, right? So as long as it does not spending time on seek and stuff, it can actually be reading and writing data for you, right? I'll go through two other policies before we wrap up for the day. So the one other policy is a scan, and the next one is a C-scan. So essentially what these policies do is, they take the hard disk keeps going from inner to outer track, right? While it's going, it reads any block it has to read on its travel over there, and then when it goes to the innermost sector, it resets back to the beginning, and then it starts to go from here, right? So sort of the way here is, so from 53, so in this particular algorithm, it's trying to go inward, so it's trying to go from 53. It tries to see all the structures which are below it, so essentially it goes from there to 37 to 14 to 0. It has to go to 0, and then it resets back, and then it goes on the other side, right? So it tries to avoid the seek problem. So essentially, the hard disk is going this way. So if you happen to be on the right, if it's moving past your track, then you get to read, or else you have to wait, right? So all these policies have the desired behavior that you would expect. So the shortest seek first, right? One of the problem is, if there are a lot of requests which are clustered together and a few which are kind of outliers, then essentially it will start them, right? There are a lot of requests which are in the few tracks which are right next to each other. Your head will essentially keep maximizing for those, and it's essentially staying right near them without ever going to the fringes. So anything written on the fringes would start. Anything in the middle tends to get good performance, and that's why you do the scan, right? Scan algorithms try to be more fair, because this column is going from one end to the other end. So you are likely to get your request in within certain bounds, either one sweep or two sweeps or whatever, right? So these things give you more fairness. Shortest job first would probably give you better performance, except it'll stop the ones on the side, right? And it's also called the elevator algorithm, because it looks like some of the buildings have the elevators where the elevators don't go back and forth, right? So if you press the elevator, it's going to the top floor. So if you're going towards the top floor, it'll stop for you, but it doesn't go down, right? It always keeps going up, and then it keeps going down. So, and that's a way to give fairness, rather than figuring out what are the individual requests, right? It gives you more predictable performance. So yeah, the C-scan is a variation where it'll come back to the beginning and then start the scan. Would keep going back and forth in either direction, right? So depending on the algorithm that you're using, you'll see different sets of seeks and rotational latency and stuff, and that's one of the things that you're trying to do for your homework assignment. And I'll say one little thing. So with the scan and C-scan, right? It'll go all the way to the beginning or the end, even if there's no request. And look only goes to the latest point. So if you had a request which only goes to, say, 37, and you're going down, right? With the scan and C-scan, you'll still go to 0 and then come back again, right? Because somebody can potentially make a request right at that moment. And look only goes to 37 and keeps going back and forth, right? And each one of them performs differently depending on what kind of request you have, which you'll see in the course of your stuff, right? And essentially that's what this slide talks about, right? So each one gives you different performance depending on what types of stuff you're doing. And we'll continue with the risk management in the next class.